Iron is element number 26. The 26 is the atomic number. It's how many protons are in the nucleus. That tells you what element it is. Same number of electrons as there are protons. And iron is number 26. So there we are. Last month we did manganese, which was number 25. And next month we're going to be doing cobalt, another good element. So we hope you come back for that. Iron, the symbol you may have noticed was Fe, and Fe comes from ferrum, which was a Latin word for iron. The Fe is from that Latin word. We just use the word iron now, which is really, really an old word. I couldn't even find a derivation for iron. It's so old because iron, we don't even know who discovered iron. It's kind of a mystery. Iron has been around for a long time. It doesn't occur naturally on the surface of the Earth. It's only in meteorite form does it occur on the surface of the Earth. So it was actually only started, they only started smelting iron from iron ore, which is an oxide of iron, about 1200 BC. And that really was the beginning of the Iron Age. Before that, bronze was the main metal, which is made out of copper and tin, which you actually can find native copper on the surface of the Earth. And before that, of course, was the Stone Age. Now, I mentioned that before 1200 BC, there was iron, but it was in the form of meteorites. Meteorites kind of look like that, or this is actually a meteorite if you want to see what a meteorite feels like. This is a iron nickel meteorite. I don't know if maybe we can get a closer shot of that. Maybe Amaris can give us a close-up. I don't know if we'll get it up onto the screen there, but our internet audience will be able to see this. Oh, there. Oh. Maybe not. Okay. Well, it looks like that. There we go. So this is actually, I love people, they say, wow, that was once in space. You realize that the thing you're standing on is in space too. So just keep perspective here. We're moving at 18 miles per second around the sun in space. This meteorite, let's see, this one was, well, sure, I'll hold it up there so you can see it. There we go. Was a meteorite that fell in 1947 in the USSR, well, the former Russia in the USSR. So that was the only form of iron that you could find here on the Earth. If you actually slice a meteorite, here's a fairly large meteorite that was sliced, and if you etch it with acid, you can see here that you get these crystals that were formed as the meteorite, the iron and the nickel in the meteorite cooled down. There's about 5 to 25% nickel in meteoritic iron. Excuse me, I'm going to get a little glass of water here because I'm still recovering from the cough I had last month. Meteorites are actually pretty expensive. They're usually in the neighborhood of like $40 a gram. They're really expensive because it's pretty rare. Here's a close-up of those etching, the crystals that you can see in meteoritic iron that you don't see if you just took a block of steel and polished it and etched it with acid. You don't see these big crystals. They're called Widmanstätten patterns. To smelt iron, you have to start with iron ore. On the Earth, iron ore occurs only in oxides. Here's a piece of hematite. That's iron oxide, Fe2O3. This is a kind of hematite called botryoidal hematite. These spheres kind of melt together as the hematite forms in layers. And if you want to come up and see that piece, that piece is up here. So all the stuff is up here. You can come and see later on. Actually, these spheres can become independent if they form separated. And there's a place that's in Utah. These are called Moki marbles, and they form on the surface of the Earth. They kind of wash out of the matrix that they're formed inside of, the rock around them kind of wears away and leaves the marbles sitting on the surface. Anyone see something like this somewhere else? Has anyone seen this somewhere else? Any space geologists here? Here, tell me if this looks the same. Those are the same kind of thing, but it's on Mars. When the Opportunity rover landed, it was surrounded by these little tiny BB-sized, well, they called them blueberries, because they have kind of a bluish cast when you enhance the color. So Mars is like, parts of Mars are just coated with these hematite spheres. And this was one of the ores, the main ore they actually used to smelt iron from. There's other really important iron minerals as well. There's magnetite. Here's a nice piece of magnetite I stole from our store. This one, if you come up really closely, you can actually see that the hematite forms octahedral crystals. The octahedrons are 8 triangles together. Oh, there we go. I'm going to show it to the camera so you can kind of see how beautiful, sparkly. You can buy this one if you want at the store after. That's too commercial, isn't it? Yeah, beautiful. And you can see I can actually stick a magnet to it. So these are magnetic. Magnetite is not magnetic. Here, I'll try and stick the magnet to the magnetite here. Hematite, sorry. Thank you for that. So if I try to stick the magnet to that, nope, doesn't stick. So even though it has iron, this is not ferromagnetic, but magnetite is. Actually, you can go out and collect your own magnetite, but not these beautiful, beautiful octahedral crystals. You can go to Ocean Beach, bring a magnet with you, bring a bigger magnet than this, and go to Ocean Beach and drag it in the sand, and you'll pick up this black sand, which we have an exhibit of right here. You can go down towards the entry to the museum in the crossroads. You'll find this magnetite, which is broken up into little tiny pieces and tumbled around by the ocean, made kind of smooth. And you can see over here on this side is the black sand stuck to the magnet. This is the magnet without the black sand. I just wanted you to see both sides there. So you can collect your own black sand at Ocean Beach. The best place on Ocean Beach is at the south end of Ocean Beach, near the zoo, or near the sewage. Weren't we going to call that thing the George W. Bush sewage treatment plant? I think there was some movement at that, but it didn't get named that. But near there, the magnetite is really, really thick in the sand. So it's a really good place to find that black sand. If that black sand, before it gets broken up, a magnetite can also sort of look like this. Oops, and it just looks like a kind of a black rock. And this they call that lodestone. This is the only rock that can be permanently magnetized, is lodestone. I don't know if you'll be able to see it there. If I put a card behind it, you may be able to see that there's actually some black sand stuck to that. Is that in focus? It's kind of hard to get in focus. But there's actually some black sand, magnetite sand, that's actually stuck to this magnet, to this lodestone. So it's the only magnetic rock that you can find. And if you break pieces of that off, each little piece is a magnet. You can float it on a cork in a vat of water, in a pan of water, and it'll point north. So you can actually use this as a compass, and that's how it was used. You can pick up paper clips with it. There we go. Oh, there we go. Pick up paper clips with it. It's pretty magnetic. So that kind of takes care of our iron oxides. It can also be used for smelting iron. But the next one is not used for smelting iron. The next mineral, which I think is really kind of pretty, is pyrite, or fool's gold. And that is kind of a really gorgeous gold color. It's not as soft as gold. It's kind of brittle, but it does form crystals that you normally don't see gold forming. Here's a piece of Here's a piece of pyrite. There's one piece of pyrite. And there we go. See how it's gold color there? We have another piece here too somewhere. There it is. This one is kind of, you can see the crystals a little bit better. Cubes, or rectangular solids anyway. Really beautiful. Here's the one with the cubes in it. But that's iron sulfide. That's not iron oxide. So if you try to smelt with this, you're going to end up with some sulfur. It's going to be a really smelly experience. How do you smelt iron? Well, you have to take a few ingredients. You need iron ore, so the iron oxide. You need carbon in the form of either charcoal or coke, which is really a carbon from coal, and you need limestone. So here's kind of the process I found online. I love it. The steps start here at the bottom. So you start with carbon plus oxygen, and that gives you carbon dioxide. And then you take the carbon dioxide and you mix it with more carbon, and you get carbon monoxide out of it. And then you take the carbon monoxide, mix it with the iron oxide, and that gives you more carbon dioxide and iron metal. And then you separate the iron from all the other constituents. In step 5, you take you get calcium oxide. I'm sorry, where is that? Molten metal falls up from the bottom. Where's the calcium in here? Oh, it was at the bottom. I missed it down here. Sorry. Anyway, eventually you get slag and iron. The slag floats on top of the iron. You drain the iron out the bottom. The slag comes out the top. And that's pig iron. It's not very good iron for what we use every day, but then it can be further refined by adding carbon or taking carbon out. So iron ends up looking sort of like this. Pure iron is kind of soft, but you really can't get it from that previous process, pure iron, because too much carbon ends up inside the iron. You end up with a little bit harder steel. The amount of carbon really hardens up the iron. The iron actually can be about 1,000 times harder. If you have carbon, it can harden it by 1,000 times compared to pure iron. Pure iron is pretty rare. We produce a lot of it, and it's produced in different countries. Here is kind of a chart of where it's being produced from 2000 until 2015. You can see we actually really increased the amount of steel that was made. Until now, we kind of leveled off, but if you see this hash-marked area, that's China. China's become a major manufacturer of steel in the world. They've really come up in the amount of steel that they've made. So, how rare is iron? Iron is actually not very rare. It's the 6th most abundant element in the universe by mass. If you look at the element in the sun, you would expect it to be pretty much the same in the sun. It's the 5th most abundant element in the sun, because our sun is kind of a recycled star. We're made out of the stuff from old stars, and those stars made some iron. So we have a little bit more iron in our sun than most of the universe does. But if you look at meteorites, iron is the 2nd most abundant element in meteorites. 22% of meteorites are iron. Interestingly enough, if you look at the crust of the Earth, it's the 4th most abundant element in the crust of the Earth. It's about 6.3% of the crust of the Earth. But if you look at the entire Earth, including the molten iron core of the Earth, it actually makes up 35% of the mass of the Earth. So it's actually the most abundant element on Earth. And if we move into the oceans, a little bit of it is dissolved in water. It's not super abundant in the oceans, about 27th most abundant in the oceans. And in us, in human beings, it's actually the 13th most abundant element. So it's right up there. There's a lot of iron in us. We'll talk about that in a moment. But where does that iron come from? I mentioned that the sun is kind of a 2nd-generation star. Iron is made inside of stars. It's the last element that stars can make by fusing hydrogen to helium, helium to carbon, carbon to oxygen, and so on. As you move up that scale, iron is the last thing that normal stars can make. iron is, and it's not made in great quantities, but it is made in much higher quantities in exploding stars. Here is an example of an exploding star. This is Cassiopeia A, and this star was first seen in the sky 350 years ago as a super bright star, probably visible during the day. It was so bright. But it's located quite far from us. So the actual explosion, even though we saw it 350 years ago, took place 11,000 years ago. It just took that long for the light to reach us. And in this is kind of a false color picture taken in X-rays. The purple part is iron. And this thing's actually pretty large. It's about 30 light years across. Another supernova that was seen in 1054 AD in the constellation of Taurus was this one, Crab Nebula. And this was actually a really cool thing. You can see it expanding. It's kind of an animated GIF here. This was done by an amateur astronomer who took pictures every year of the Crab Nebula starting in 2009. And he's taken one every year, and by doing that, you can actually see the supernova expanding. It's an extraordinary set of pictures. I mentioned that iron is the last thing that stars can make. On this chart, iron, you start off with hydrogen here. If you combine hydrogen to helium, you get a lot of energy out. The difference between the energy here is quite a bit. But then, as you move up this thing, you're getting less and less energy as you're making heavier elements until you get to iron at the top here. Past iron, it takes more energy to make the other elements than it does it takes more energy to make them than you get out of them when you fuse them together. And so stars only make up to this. Well, where do all these come from? These come from the supernovas, where all that energy from the collapsed star is available, and you could actually make new elements all the way up to, well, in this case, on this chart, uranium. So it makes a lot of different kinds of elements in a supernova. And iron has lots of different forms. I mentioned that it always has to have 26 protons in the nucleus, but can have different numbers of neutrons. We call those isotopes. So this number that you see up here, 51, 50, 49, 48, that's the total number of protons plus neutrons in the nucleus. That's sort of close to its atomic weight. And these are all the different kinds of iron that are made inside of stars, but they're not all stable. There's only 4 of them that are stable. So iron 54, 56, 57, and 58 are stable. They're not radioactive. The rest of them are all radioactive. So these occur in different proportions. The most common is this iron 56. 91% of the iron in the universe is iron 56, with much less of the other isotopes. All the other ones, radioactive, and here's the ones that are sort of the least radioactive, the longest lived. So iron 55 has a half-life. It takes, no, I'm sorry, iron 60 is the longest lived. It has a half-life of 2.6 million years. If I had a lump of iron 60, it would take 2.5 million years for half of it to decay. And you can see the other ones, 44 days, 2 years, 8 hours. All the rest of them are like under a minute. So these are the longer-lived isotopes. So iron has lots of different forms of the same thing, isotope, but only 4 of them are stable, and these are the most stable of the radioactives. What else can we say about iron? Oh, its density. Iron is middle density, 7.8 grams per cubic centimeter. Remember what water is? 1 gram per cubic centimeter. And I've listed a few more down here. The densest element is osmium, but the densest we have on the table here, and I invite you up to try to to play with the density of these cubes. On the table here we have, let's see, we have tungsten, we have lead, we have copper, we have steel, iron, we have titanium, we have aluminum, we have magnesium, and then the ones that are not on the chart here, there's iron right there. We have plastic and maple. So I gave chemical. PL is plastic. It's actually not an element, so I can do that. Ma is maple, so it's not an element either. So play with these. If you're going to play with the tungsten, however, it's very, 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 very dense. Get your hands underneath it before you lift it, because it'll be surprisingly heavy for its size. As a matter of fact, tungsten has the same, almost virtually the same density as gold. So a gold brick that size would weigh the same thing as that tungsten brick weighs. So, but just be careful if you're going to try and lift it after. I mentioned it's kind of soft. Pure iron is kind of soft. It's on the Mohs scale of hardness. It's right there. Has a hardness of 4, which is not really hard. You could scratch it with glass. Steel is a little bit harder, about 4 to 5 on this scale. It's right below there. It's a relatively abundant element. If you had to buy it, 25 cents a pound, pretty cheap stuff. It has a pretty big atom because iron has all these electrons hanging out along the outside. It combines with a lot of things. So the atom of iron tends to be fairly large compared to the atom of hydrogen. Its spectrum is really cool, though. This is the periodic table of the spectra. And iron is right there. And it has a really complex spectrum. There's thousands of colors given off by iron. If you look at the sun, the sun has an atmosphere that blocks certain colors depending on the elements in the atmosphere of the sun. Here's the spectrum of the sun. All those dark lines are caused by elements in the atmosphere of the sun, and the vast majority of these dark lines you see up here are iron. I've labeled just a few of the ones that are actually iron. It takes quite a while if you want to do all of them that were iron, but virtually every line up there is iron. There's a few exceptions. I mean, this big dark one here is hydrogen, sodium, hydrogen, but it's a very effective tool. You can actually tell what the sun is made of without having to go to the sun and scoop up a sample of the sun. Spectroscopy. Lots of uses for iron, of course, in industry. Model T was made out of iron. He actually made an alloy of iron and vanadium, much stronger, so he can make the car with less steel, cheaper, lighter. All the tools that we have in our shop are iron, pretty much, or various alloys of iron. These wrenches up here this is the 4th time I've been able to use the wrenches, because it's an iron alloy with vanadium and manganese, and they're chrome plated. So this is the last time I get to use the wrenches. Now I actually have to use the wrenches as wrenches. Everyone's used this stuff, right? That's iron. This is just an iron. This is steel wool. Here I have 2 different finenesses. What would you call it? This is, oh, sorry, I didn't know you were going to do that. There's a coarse one here and a fine one here. And that's what you saw kind of magnified up on the screen. I just put them on the scanner, scanned them on the scanner. So that's the coarse stuff here and the fine stuff here. Have kind of sharp edges to the fibers if you look closely. If you add elements like vanadium and manganese and chromium into the steel and make an alloy, you can make stainless steel. This keeps oxygen from reacting with the steel. All of our pots and pans at home are usually made of stainless steel. Iron's been used for quite a number of things. You can go way back. Of course, we have the Iron Maiden. Not this Iron Maiden. By the way, the Iron Maiden was a myth. It was made much later than the Middle Ages. We have, of course, the Iron Horse, Iron Man, and of course, the iron. And there's some antique ones, and they were made of iron. You had to heat them up above a flame. Iron is useful because it's ferromagnetic. You can magnetize it. Here's 2 kinds of magnets. On the left are ceramic magnets, which is really an iron, kind of an iron oxide that you can magnetize. And on the right is alnico. It's mainly iron, But it also has aluminum and nickel and cobalt. So you're going to see this one next month too, because it has cobalt. Of course, not only cars, but our beautiful Golden Gate Bridge, excuse me, is made of iron as well. Here's just at the beginning of construction of our bridge. The giant suspension cables are made up of thousands of little tiny steel cables that are compacted into one big cable. Of course, it ends up looking like this. The Golden Gate Bridge has about 800,000 tons of steel in it. It's a lot of steel. Of course, it's been useful in war as well. When they finally figured out how to do it, ships got an iron skin. So this was a ship from the Civil War, the Essex, part of the Union's Mississippi River Fleet. And nowadays, of course, virtually all ships are built of iron in one way or the other. During the war, if I can stick with the war theme here, copper was was needed for the war effort, and so pennies could no longer be made out of copper. They needed that copper for the war effort, so the 1943 penny was made out of steel. It's the only magnetic coin is the 1943 penny. So if you come across a steel penny, it better be a 1943 penny. Steel does have a problem, of course. It chemically combines with oxygen in the air, and it rusts. This is a can from an exhibit we have that's over by the bio area there called Just Rust. These cans were actually in the basement of the California Academy of Sciences for I don't know how many decades, and they made these and they rusted into these beautiful, beautiful rings. We rescued a few of them from the academy when I used to work there, so really kind of cool. One thing about rust, though, is the rust takes up more room than the metal that it started from, and so that can be a problem. This is an exhibit that's outside called the Rust Wedge, and if you look closely at the Rust Wedge, there's a bunch of iron here that's rusting away, but the iron is taking up more and more space, and so if you magnify, it's pushing this apart and cracking the cement block. So if you let rebar inside of cement rust, it's going to expand and actually break apart the cement, so it's a real problem. These guys here, you don't have to have the camera on this. These hand warmers, I don't know if you've seen these hand warmers. Let's open one up and pass it around, because this works by rusting. These packets here, see if I can get this other one open. There we go. So these packets have, should have practiced this one. I'm going to shake them up here. Inside of them, if you look at the contents of the packet, contains what? Iron powder, water, salt, activated charcoal, and vermiculite. There they go. They're beginning to get warm here. You can pass them around. You're going to actually feel them get warm. You get to feel the rust actually happening. The rust happens so fast in these packets that they keep you can keep your hands warm with them. It's kind of cool. Or kind of warm. In your body, we have iron plays a really important role in biology. In your body, it forms complexes with molecular oxygen in hemoglobin, so it's in your circulatory system, and the myoglobin, and these are the things that are responsible for carrying oxygen from your lungs into the rest of your body. It also is part of, aids in the synthesis of DNA, and it helps also scavenge free radicals from your body. So iron is a pretty important element in your body. I want to end with I found a really wonderful collection of elemental haikus. So here's the elemental haiku for iron. Anvil, axe, nail, plow, engine, railway, factory, servant, friend, partner.